Hello students. In the previous lectures, we have previous lecture rather, we have discussed what is vector function, scalar function, uh, how do we find the limit of the vector function, how do we differentiate the vector function. Now in this lecture, we'll discuss types of vector functions. Type vector function is vector function, constant vector function, kinds of constant vector function, construction whose magnitude direction same. If magnitude is same, we get different vector function. If magnitude is not constant, direction is constant, we'll get different type of vector function. So we'll discuss them first, then find their relative properties. So let's define three type of vector functions. First is if a vector function whose magnitude and direction is fixed but do not change, whose magnitude and direction is fixed but do not change is called constant vector function. A vector function whose magnitude direction remain the same is called constant vector function. So for example, let OP is a point in this Theta's Cartesian plane whose coordinates are G, 3, and 0. So OP is the position of the point P in Theta's space. So OP is Ft vector. Ft vector is equal to 3 iota plus 3j minus 4k is a constant. Now it's a constant vector. Constant vector. So now modulus of Ft vector is equal to 34 is constant. Magnitude of Ft is constant. Now, since Ft represents the position vector of a point, this point 3 whose order is equal to 3 minus 4, so the direction of Ft is fixed, means it's equal to O to P on the inverse. So this vector Ft, Ft the position of the point P in this three-dimensional plane is OP is a constant vector function. Now, another function, vector function with constant magnitude but direction is not constant. So this is another type of vector function whose magnitude is constant but direction is not fixed. So that kind of vector is, let us take Ft vector is equal to iota cos t plus j sin t plus sin t. Magnitude of this vector is equal to x square cos t plus sin t plus 1 square root is equal to 1 plus 1 root 2. So magnitude of this vector is constant, fixed, constant. But the direction of Ft vector is not fixed as it changes when the value of the scalar variable p changes. When p changes, the value of this Ft will change. So this vector Ft vector is equal to cos iota vector plus cos sin t vector plus a is a vector which has constant magnitude but direction changes with the value of as the value of p changes. So this is not a constant vector. This is a vector with constant magnitude and have and does not have a constant direction. Fixed direction. A vector function Ft vector which has constant direction but no constant magnitude. So for example, this Ft vector 2t iota plus 3tj plus 4tj is a vector. This can be t is common. 2 iota plus 3j plus 4k into t. Now the magnitude of this vector is equal to 2t square, 9t square, 16t square, and root of this is equal to 29 and root 29t. So magnitude of this is equal to t. T means the scalar variable. If scalar changes, the magnitude of f vector changes. The above equation implies that the magnitude of Ft is different for different values of t. Therefore, ft has no fixed magnitude. But the direction of ft is fixed as it coincides with the direction of this vector. This vector means 2 iota plus 3j plus 4j for all value of t. So now this vector OP T if you increase this bond increasing and but in the same direction. This vector whose magnitude is not fixed but direction is fixed. So we have three types of vector function. Vector function whose both magnitude fixed. Second is whose magnitude fixed but direction is fixed. Third is whose magnitude is not fixed but direction fixed. So three types of vector functions. This case was not in case of the scalar point function which we discussed in the differential calculus of first year. Now let's try it. Let's find how to find the vector constant vector function. Show that the derivative of a constant vector function is 0. So the same result, the derivative of a constant in the scalar point function is also 0, and same result holds true in the case of vector function. Let r is equal to 0. This is a constant vector function. Constant means the magnitude and direction of this vector function is same. Constant vector means the magnitude is same. This is a position vector of any point in the direction at any time t. Now at time t plus delta t, the position vector of the point changes. This is r plus delta r is equal to 0. Subtracting second from first, we got delta r is equal to 0. Dividing both over delta t, the change in time, and taking them delta to 0. This is equal to implies limit delta t to 0 of del r upon del t into dr dt differential r to t at any time t. The derivative is equal to 0 implies derivative of the constant function is equal to 0. Now derivative of vector function in terms of components. So if vector is in components, how can we find the derivative of that function? Let r be the position vector function of the point of scalar point function. Okay? So that is r is the function of x iota yj. X, Y, Z are the scalar function of time, and I, J, K, I, K are the fixed in vectors. Therefore, differential of first these two t will be dr dt is equal to derivative sum derivatives differential formula of differential is the same here in the as in the case of differential calculus. In the vector calculus, formula of derivative are same as the of derivative of the vector calculus in the solution differential calculus. There's some derivatives, derivative product is first function, derivative second, and so on. Like the first function, derivative first, second is derivative first is derivative second, and so on. All the time there's some there's some, and then product using this. Now derivative from iota j k are fixed vector, derivative equal to the constant vector derivative 0. So derivative of a derivative vector in component form is equal to derivative of the component. Derivative of the vector in component is equal to derivative of the vector. So if you want to find derivative vector, find derivative of components, and this will give you